Hello everyone. So we've got a lecture today on Mergesort, and then tomorrow we're going to be doing the review lecture for the midterm. One thing I wanted to point out is that there is a skip in the lecture numbers just because of where the Memorial Day holiday fell this year and stuff. We're going to do what is normally lecture 13, strings and sequences, near the end of the semester. And if you look at the schedule of topics, I renumbered them slightly just because it was just easier to leave the slides the way they are with the lecture number in the slides than edit every slide and then edit them all again next semester. So lecture 13 will be out of order, but we will get that material in near the end of the semester. And we have time. We're not cramming things into, two topics into one lecture to make it happen. It's just that we wanted to get the midterm before the end of the week and then give you the project specs so that you could start looking at it. So today we're going to talk about Mergesort, and we're going to look back a little bit in retrospect at Quicksort. So the idea of Quicksort is, let's take what we have, some unordered collection of stuff, and partition it into two segments. The smallest elements and the larger elements, and we have to pick a value to do that. And that picking of the value isn't always perfect. And so we end up with two different, we say halves in big air quotes, but they aren't necessarily halves. They're two regions, the small portion, the big portion, when we hope that they're halves. In the best case, they are halves, but not necessarily. The Mergesort takes the idea that, well, what if I had two sorted regions? If I had two sorted regions, I could merge those two sorted regions together into one sorted region that's twice as big. And we build that up from basically size 0 or 1 combines into size 2s, combined into size 4s, etc. So here's the sort of basic pseudocode outline for the two of them. So Quicksort says you give me an array to sort, and I will partition the array first, then I'll recurse into the left half, recurse into the right half. Mergesort puts the non-recursive call last. We merge sort the first half, merge sort the second half, and if we make the assumption that Mergesort does do its job, then once it is done on the left half and the right half, then we can merge those two halves together into a larger sorted region. Now, like I said, in the Quicksort, we say left half and right half. We hope that they are halves. We could say like smaller values and larger values, but then that gets away from like, well, what if I want a descending sort? So there's no perfect term for this. So just remember, when we say Quicksort left and right half, we hope that they're halves. In Mergesort, we're going to guarantee that they are halves. We're going to pick the midpoint specifically. So we can write these both with a top-down approach, and we're going to see later on that Mergesort we can actually do with a bottom-up approach. The important thing is that regardless of the approach, regardless of how the code is written, nothing gets done until we get down to those small regions. Whether we start with the top and say, hey, I've got a big thing I want to sort, well, let's imagine I could recursively sort the first and second halves, then I could merge them together. And then we take that intuitive, inductive step of, well, let's assume that if we assume that the smaller calls do their job, then we can assume that all the way down. But nothing really happens until recursive calls get done and get those smaller regions actually merged together before we get bigger regions. Now let's go through an example here that's showing how Mergesort works. And this is the top-down code that we just looked at. So it says, well, I would like to merge sort the first half. That recursive call to the first half of Mergesort has to finish before with the call to the right half. So we make the call on the first half and we have to finish it. Okay, so I make a recursive call on the left half. So now I have a region of size 4 that I want to merge sort. the first thing it does is say merge sort the first half. Okay, I've got a size of 2. Let's merge sort that first half. Well, now in pseudocode is nice because it's pseudo-correct. The pseudocode didn't have a base case, which, if we're doing recursion, we really need a base case, right? Our base case is the same as Quicksort. When I have a region of size 0 or 1, I'm done with this base case. So we make a recursive call to the left half, that one element. That recursive call says, oh, I'm a base case. I'm done. I am a sorted region of size 1. All right, well, that first recursive call finished. Let's make a recursive call to the second half of the size 2 region. That's a region of size 1. That's a base case. I'm done. And the recursion unrolls. So we're now back to the region of size 2. The region of size 2, now that both halves have been merge sorted, can now do step 3. So this was basically, if we call the previous slide, if we call this like step 1, step 2, steps 3, what we're seeing over here is this was step 1, step 1, step 1, step 2. And now what we're going to do is merge those together. This is step 3, the merging together. Now, where do we go next? There's recursive calls on the stack, right? There was main, at least, was on the stack, and main at least called someone who called merge sort. Merge sort called merge sort on the first half region of size 4. It called merge sort on the first half of size 2. That call has finished. Now we make step 2 on this size 2, the region 4, 7. Okay, so I do step 2. I say recursively call the right half. Now, recursively call into the left half. Step 1, that's a base case. Recursively call the right half. Step 2 is a base case. I've finished both the left and right halves of this region. Now I can go on to step 3, which is merge those together. Now this recursive call is done. It returns to the caller, which is where? Up here. That one says, well, I've recursively sorted the left half and right half. I can now merge those halves together. That's another step 3. Let's merge those together. And if you picture this, we sort of ran through it real quick there. What would we actually do when we merge these together? We'd say, hey, let's start. I'm going to have to erase that 3 for a second. If I want to merge two things together, I would have to say, hey, let's start here and here. The smaller of the two goes to the output, and then we move that one forward. Smaller of the two goes here, move that one forward. Smaller of the two goes here. Oh, look, I'm off the end of the first container. Everything from the second container moves down here. So that's how we did the merging. We haven't written it yet, but we're going to have to make that happen. Okay, let me erase that so we don't have it over the top of the animated slide. Okay, whoops, no, I didn't mean to draw with my finger. Okay, so that was our step 3 there of merging. Now we are back to the top, to the very original call to the region of size 8 has finished its recursive call to the left half. It can now make a recursive call to its right half. And now all those things happen again. Recursive call to the left half, recursive call to the left half. Oh, look, that's a base case. Return, recursive call to the right half. Both recursive calls are done. We can merge together. Second half of the region size 4. So 6-1, recursive call left half is a base case. Recursive call right half is a base case. Both recursive calls are done. We can merge the regions of size 1 into a size 2. And now we can merge those regions of size 2 into a region of size 4. And I underlined one of the ones so we can keep track of the two different copies of one and see when we merge those together. Well, we would take the smaller one, right? I'm looking at this one and that one. I take the smaller one. Well, they're the same size, So let's take the left one. So I get 1, 1, 3, 6. Now that was somebody's step 3, but it was also finishing the step 2 up here. So now we can go to step 3 for the whole thing. We have finished left half of the original 8, right half of the original 8. We can now merge those 2 regions of size 4 into a region of size 8, and we get 1, 1, 2, 3, 4, 5, 6, 7. So that's how Mergesort works. That's watching the order of the recursive calls and the merges. Now, let's look at some things about Mergesort. So Mergesort was created as an external sort, and I think I typed this in the chat in a previous lecture. Mergesort was invented back when there were magnetic tape drives. And imagine if you've ever seen like a picture of a cassette tape, go back before that. There were reels of tape. They were about yay big, like 4 foot in diameter, about an inch wide magnetic tape, and one of those could store like 32 kilobytes. But that was huge because the computer's main memory was like 4 or 8 kilobytes. The problem was people wanted to do things like they're doing now. They wanted to have like a list of employees and sort it. But the list of employees for just a moderately sized company and, what department they were in, etc., didn't fit in memory. We had to sort them even though they didn't fit in memory, so they came up with Mergesort. And Mergesort would literally have like 3 big diameter tape drives running. And of course, there were 2 reels. There's the reel that the tape is coming off of, the reel that it's going onto. It passes over a read-write head. That's sequential access. So you would read employees from like this tape and you'd put it on 2 other tapes. You'd split it into 2 regions. And then those 2 would merge and they would overwrite like the first part of the first tape. And then we'd do that back and forth. We'd say, okay, take the second region, split it into 2 halves on 2 separate tape drives, and then merge those back. And it was just like insane to do, but it happened. And you might say, oh my gosh, Dr. Paley, that's just crazy. We don't use tape drives anymore. We've got DRAM and we've got flash memory. And your flash memory is like a 10 terabyte flash drive, but you've only got 16 gigabytes of main memory and RAM. So the problem still exists. Generally, one company doesn't have to sort over 16 gigabytes of data for their employees, but companies like Google, they've got a data set that's petabytes large and is split across different servers. So Mergesort was designed for the idea that, hey, the external memory is much bigger than internal memory, and so there's still useful things to learn from this. So that was what it was designed for. The items are accessed sequentially. Now, we can write it with arrays, but we could also write it with linked lists. So the idea of this one is when we sort, there's 3 categories that we can put it in. There's the sort in place with no extra memory. There's the sort in place, but I'm going to say leave the data alone. I'm going to make a smaller block of memory, the same number of elements, but instead of like these big 10 megabyte medical records with images, I'm just going to sort people by this array of like dates and pointers or dates and indices at which they were seen. And I don't know where Professor Darden is. And yes, this is going to be on the midterm. Okay, so then that would be the second one. The third one is we need enough memory for an additional copy. That's where Mergesort comes in. We're going to have an additional copy to make the merging happen. All right, now we're going to show you something that you may have not seen before called the ternary operator. So C++ has lots of binary operators, lots of unary operators, like plus and minus and times and divide are binary operators. They have 2 operands. There's unary operators, like minus is a unary operator. Also, I can say like a is equal to -3, so that's a unary minus. There's plus plus, minus minus are unary operators, and there is the ternary operator because there's only one that has 3 parameters. So we've got a statement up at the top, and we've got a translation of it down at the bottom. So that one statement at the top is equivalent to those, let's see, 1, 2, 3, 4, 5, 6 lines of code and 2 lines of curly braces. So 1 line of code equivalent to 6. This is where we get into that fight between terseness or shortness and understandability. And some places the ternary expression is so short it's used because it makes these 6 lines of code fit into 1. There are some places where you can't not do without it. And I'll show you one in a second after we understand it. So what this is saying is, if a sub I is less than or equal to b sub j, set c sub k equal to a sub I, and then increment I. Otherwise, set c sub k equal to b sub j, and then increment j. So the ternary operator says, first of all, we have a test, a conditional, to make a decision. And then, if that condition is true, we do the second operator, or operand, sorry. So the first operand is the condition, second operand is what to do if it's true, and the third operand of the ternary operator is what to do if it's false. So we say set c sub k equal to the result of the ternary expression. If the ternary expression is true, this region is evaluated, and then is the result of the ternary expression is a sub I, and I gets incremented. If the conditional was false, then this would be the clause that's evaluated. C sub k gets set equal to b sub j, and then because it is a post increment, the increment happens last. Now in these lines, we could have done it as a pre-increment or post-increment. It doesn't matter. It's on a line by itself with a semicolon and nothing else. But up here, these have to be post-increments because we want to grab what's currently in a sub I before I gets incremented. And if the ternary expression is true, j does not get incremented. There is a set of slides for the midterm, and that's one of the things in there. Like there's what's going to be on the midterm and the structure, and then there's a section on what counts as a line of code. So you could look at that after today's lecture, or we're going to go over it tomorrow. So we'll go over all of that. All right, so this is the ternary operator. Let me give you an example of where it would be required to have a ternary operator. Let's say in project 2, part A, I'm doing PR mode or TL mode, and I don't want to make a function for processing transactions. I'm like, hey, I'm in main, I've already created this vector and that vector, and I just want to do everything in main. Okay, bad decision, but okay, since you're already here, I will help you write less code. Instead of writing the input code twice, once for the string stream, once for the CN, what I could do is I could say, I've got an iStream reference, and let's call it in. I'm just going to call it in because I'm running out of room here. I'm going to set it equal to is mode equal to TL question mark. But then I will set input, my iStream reference will refer to CN, else, set it equal to SS my string stream. And then I can write my while loop. I can say while in goes into variable 1, that's variable 2, etc. And that's my while loop. So there's my ternary expression. So we got a little too long there. So this is a way to make a reference variable refer to one of two things, but we can't do this without the ternary operator because you can't say iStream reference in semicolon. That's invalid. reference variables must be assigned, we must refer to something when they are created. They can't be created and then referred to something later. It must happen all in one line of code, so the only way to do this is either the ternary operator or member function, or standalone function would work too. All right, so that's a why we would have to use the ternary operator in some cases. Okay, so the ternary operator is going to be this one line of this bigger function. So here's merge. So this one's called merge A, B. It's basically saying I'm going to merge A and B into C. So C is where I'm going to merge to. And then region A of size A and region B of size B, these are where I'm going to copy from. So I'm going to take things from A and B, I'm going to put them into C. This function makes the assumption that C is big enough to hold both A and B. Right? If it's not, that's not merge's fault. That's somebody else's fault. So this says, I've got I and J, and I had to do this in multiple lines. I could have done it all in one line if it had fit on one line. I could have said for size T, I equals 0, J equals 0, K equals 0. You can put commas in there. So you can say size T, I equals 0, comma, J equals 0, comma, K equals 0. But that didn't fit on one line. So separate it up a little bit. So I've got I and J are 0. And basically I is the index into region A. J is the index into region B. So you'll see right here I say B subscript J, A subscript I, A subscript I, B subscript J. So that's what I and J are. They are the indices into array A and array B. Okay, so this loop says I'm going to have to go through everything in size A plus size B. So if I had regions of size 4, 2 regions of size 4, loop's got to run 8 times. I've got to copy 8 things out of A and B, 4 out of one, 4 out of another. So I'm going to run for k equals 0 up to just less than the size of A plus B, and that gives us an index. K is an index, inclusive, exclusive. When k is equal to the size of A plus B, the loop stops because that would be an invalid index. Okay, and every time through the loop, we're going to increment k. Now it says if I is equal to the size of A, this is basically saying if we reach the end of region A, well then what goes into C has to come from B. All right, and then else if J equals to the size of B. So else if I'm at the end of region B, what goes into the output has to come from region A. Else, it says what goes into region C is the smaller of them. So we take the smaller, if we're within the range of both containers, we take the smaller one, else we take from the container that we haven't finished yet. So that's the merge. Merge says you give me 2 input arrays and an output array, 2 input sizes, and I hope the output size is big enough. I will merge those 2 sorted regions into one larger region. Now, this is a little bit painful because it requires us to have all these like 3 separate arrays. Didn't I? I really wanted to sort like one array, right? I wanted to have I didn't want to have 2 separate arrays, A and B. Really what I wanted is I want an array with region A and region B. We'll get there in a little bit. We'll get there soon. Let's look at how the merge works now. Okay, so here's an example, and we did an example where what if the sizes weren't equal, right? What if we had a region of size 7? Well, we split it into regions of size 4 and 3. All right, so we split it into 2 regions, and we have recursively gotten down. So these regions have recursively been sorted. Now it's time to merge these 2 together. All right, so remember we started out I is 0, J is 0, K is 0, and we run through. So it says when k is equal to 0, A sub I, where I happens to be equal to 0, well, A sub 0 happens to be equal to capital A. So that's what that notation is showing you. It's sort of like a combination of the code and showing you what values the variables have right now. So a sub I, which happens to be a, is that less than or equal to b sub j, which happens to be the value b? Is a less than or equal to b? Yes. So then what we do is we take, since the value in region A is smaller than the value in region B, the value from region A goes to the output. Okay, and then I gets incremented because we took from region A, I gets incremented, and then K always gets incremented. So when K is 1, we're comparing D to B. Is D less than or equal to B? No, so take from region B and then increment J. Okay, now we're at D and D. Is D less than or equal to D? And I know there's colors here. I believe they are gray and maybe they used to be purple. In the updated slides, I'm not sure. We'll go with purple. You can pretend I said the right color if that's wrong. Or you can type it in the chat and I'll correct myself in a minute. Okay, so is the gray D less than the other one? Well, less than or equal to the other one. Yes, it is. It is less than or equal to. So the gray D moves to the output. And I gets incremented. Now, is G less than or equal to that darker D? No, it's not. So the D from region B goes into the output and J gets incremented. K is 4. Now, is G less than or equal to F? No. So F goes to the output, J gets incremented, and now J is off the end. So we said, hey, because J is equal to the size of B, then we copy from region A, we copy the G to the output, we increment I is still equal to the size of B, so we copy H to the output, we increment I, K gets incremented, and the loop is done because K has reached 7. So we got everything from those two sorted regions merged together into C. Okay, so that's how the merging step works. And what we can do is we can write some more code instead of pseudocode. This is really close to real code here. So I've got an array called item of items, whatever item is. It could be ints, double strings, employees, structures, student classes, whatever. So I've got an array of items. I've got a size t left and a size t right, and it is, as we said before, from now on we're going to stay with left is inclusive, right is exclusive. So that's the original sense of the left and right we are given. And so what we say is, let's check if it's a base case. Real code, we got to have that checked. Pseudocode, we skip that part. So real code, if right is less than left plus 2, we could say if left plus 2 is greater than right, etc. It's just getting down to, do we have a region of size 0 or 1? Then we can return. We're down to a base case. So if we've got a base case, we could also say if like left plus 1 is greater than or equal to right, would be another way to say it, whichever way makes sense to you. So then, if we don't have a base case, let's figure out where the middle is. And it is the exact middle or one off if there's an odd number. So we figure out the middle, and then we merge sort A from left to middle. And this is the sense, left inclusive to middle exclusive. And then from middle inclusive to right exclusive. So the middle only gets included in one region. The middle gets included in the right half call. And then there's a merge here, but this isn't merge AB. This is slightly different. This says merge. I'm going to just give you A. Here's what I want sorted, or sorry, here's what I want merged. I want A merged, and I want it in the sense left mid and mid right. So merge is we're going to have a slightly different version of merge that takes different parameters. There's only one array, but there are 3 indices. And these indices, we could change this to be iterators if we wanted to. We could change it to vectors. We could change it all to iterators if we wanted to. So we've got array A, left to middle, and mid to right are the two regions of A that need to be merged. So we need a slightly different version of merge. Now it says at the bottom, so it says it's a prototypical combine and conquer. So it says really the order of operations is conquer and combine. But because we called it divide and conquer, someone decided to call this combine and conquer. But really, I think a better name would be conquer and combine, because that tells you the order that we do things. You can think of divide and conquer as a superset of combine and conquer. Combine and conquer is like a subset of divide and conquer. So like it says, we do the recursive calls to size 0, 1, then we merge them together. And the question is it safe to use recursion here? Notice we've got two calls that are not tail recursive, which means they need stack frames. So the question when I say, is it safe to use recursion, is what I'm really asking is, could we get a stack overflow? Well, let's say I had 1 billion elements to sort. Because we divide it exactly in half, or off by 1 at most, because we're dividing in half, not partitioning and hoping that they are halves, but really picking the midpoint. If there were 1 billion elements, log base 2 of 1 billion is 30. We would need 30 recursive calls to sort 1 billion things. Even if there were 1 trillion, we would only need 40 recursive calls. So not too bad. So that's the beauty of recursion when we know that it really is splitting it into 2 halves and not hoping that they are halves and maybe getting sizes of 0 and n-1 like Quicksort can manage. Okay, so it's safe to use recursion. So here's a modified merge. What's modified about it is basically, hey, let's make a temporary vector, and then let's merge from A and B, or really not A and B, from A the first region and A the second region. Let's merge from A's left region and A's right region into C, and then when we're all done, it says copy the vector back into the array. So the downside of this one is we have to make that extra block of memory ourselves. So we'll talk about memory complexity in a little bit. So we have to make that block of memory, and we have to clean it up when we're done. We could have done it with new and delete, but it was 1 line less code to do it with a vector and let the destructor clean it up for us. And safer, because if I write the new and forget the delete, bad things happen. Okay, so we figure out what n is. So n is right minus left. So if you think of our original one, like, hey, the example we did a few minutes ago where there were 7 items. Left would have been 0 and right would have been 7 because it's 1 off of the end. If there's 7 items, they are 0, 1, 2, 3, 4, 5, 6. 0 through 6 are the actual indices. 7 is off the end. So then the size is 7 minus 0 is 7. And then when we get into subregions, we might say, hey, I'm going from like index 3 to index 6. Well, 3 to 7. I'm going from 3 inclusive to 7 exclusive. That's a region of size 4. So this will take care of the exact size of the subregion, no matter where we are in the recursive calls. It says, make me a vector of n items. And this one assumes that the items are default constructible. We could write this with a reserve and a pushback. We could rewrite this with reserve and pushback. Might be a little bit safer and would make sure that we don't need default constructors. And it might save a little bit of time. Okay, so we say make the vector, and then the rest of this code is exactly the same. That came out of the code for merge. Almost. Remember, we don't have A and B anymore. So it's A in region J is the second half. So A sub I is the first half, and A sub j is the second half. So we're copying from A region I or A region j goes into the output C at index k. So it's almost the exact code from the previous one, except it's instead of B sub j, it's A sub j. They're two regions of the same array. So we put stuff into C, and then when we're all done, we use the STL, standard : copy, to say, hey, this is the from inclusive exclusive. Those are the inclusive exclusive. And this is the to inclusive. And it makes the assumption that where we're putting it is big enough to hold it. Okay, so we're copying from the beginning of the vector to the end of the vector. So that's the whole vector. So the whole vector gets copied back to, wait a minute, address of A sub left? Okay, let's figure this out. Okay, so let's say I had A. A is this array. Okay, so there's 7 indices. So this is the array. Let's change this just a little bit. Okay, so this is A, and this is index 0, 1, 2, 3, 4, 5, 6. All right. So I made a recursive call, and recursive calls ended, etc. So let's see what would happen. So we'd say the 7 plus, so left plus right minus left over 2. So the middle would have been basically, we would have made a recursive call to 0 to 3, and then we would have made another recursive call to 3 inclusive to 7 exclusive. 7 is just off the end. So let's think about when we've merge sorted the second half, right? I've got the second half from index 3 inclusive to 7 exclusive. I've done the recursive calls, and now I have to merge these two regions of size 2. Two regions of size 2. Let me change colors here. I've got to merge two regions of size 2 into a region of size 4. So I make the recursive call that, or I make the call to merge that says take 3 to, basically 3 to 5 and 5 to 7. Let's merge those. So 3 to 5 inclusive exclusive and 5 to 7 go into C. So if, let's say this was, let's look at the example just a second. So it was BDF, right? So this is BD, oh, whoops, I guess we did that slightly off. Okay. Oops. So, yeah, I guess our other example is slightly off because the second region would be the slightly larger one. Oh, well, anyway, let's see. Let's say we had A, B, and let's do A, B, and AF, for instance. Let's just make it slightly different. So I've got A, B, AF. That's underlined A. So we could put those into C. So C gets A, underlined A, B, F. So we put those into C, and then we have to copy it back to A. But standard copy needs to be given an iterator. In this case, a pointer. Arrays are pointers, pointers are arrays. So we say, I want to copy it into A, starting at index left. Remember, this is the left in our call. This is left, this is right of our original. So we want to put it starting at A sub left. So we say A sub left, and then take the address of that. If you want to, you could add parentheses around this to make it clear what the order of operations is. The subscript has higher precedence. So the square brackets operator has higher precedence than ampersand. So square brackets happens first, then the address of is taken, and that's our pointer to there, is where we're going to copy to. So we're going to copy from C, begin and end, to the region starting at A sub left, the pointer. So that's what that's doing there. It's getting it back into A, and then the function ends. Vector destructor runs automatically and cleans up C. So we had to make that extra region in there, that extra vector, that extra block of memory to do the merging. So, summary of merge sort. So this was the top down. Remember, we started with a big picture and said, well, let's recursively call, let's merge them together. So this sort, it says it's O of n log n. Well, wait a minute. It says it's O of n log n. Let's prove that to ourselves. All right. So this is slide 12. We're going to have to go back a ways to our code for merge sort. There's our code for merge sort. Okay. So here's our code for merge sort. Well, we've got a T of n is equal to T of n over 2, that's the left half, plus T of n over 2, that's the right half. They really are halves. And then when we're done with those recursive calls, we have to merge them in merging. It says merging takes size time n. Wait, do we even believe that? Okay, let's go do that one. So do we believe that merging takes time n? Well, I've got a for loop that runs n times. Every time through the for loop, we move forward in the output. The output is of size n. Every time we go through that loop, either I gets incremented or j gets incremented. So we're making progress on one input or the other, and we're always making progress on the output. Well, the size of the inputs total to n, so I and j combined must move n times. K must move n times. Well, it does. K moves every time the loop runs. So yeah, so the merge step is O of n. So if we believe that the merge step is O of n, then we've got that. So I could say, well, this is just equal to 2t of n over 2 plus n. We can throw that in the master theorem, and we get big theta of n log n. All right, so go back to slide 13. So our summary of fast, n log n, we can believe it now. We did the master theorem. We solved where we wrote the recurrence relationship, used the master theorem to solve it, n log n. And it really, I suppose we should say big theta here, because this is exactly, it's always n log n. Doesn't matter. Best case, worst case, average case, it's always n log n. Now it says it's stable when a stable merge is used. And there's a hint there in parentheses, hint, it's always used. What made our merging stable? Well, what made our merging stable was right here. When we had to choose between the D's, we said less than or equal to take from the left half. Well, because we had the left half, right half, if they're equal, if it's D and D, if we take from the right half, or the left half, I'm drawing it your way. So if we take from the left half, the D we get must have been the first D. So merge sort will be stable as long as the merging step is stable. The merging step is stable as long as we put less than or equal to there. As long as that merge is stable, then merge sort is stable. So we always want to make sure we put less than or equals there. Whoops, that went to slide too many. Okay, so it's stable as long as the merge is stable, and we make sure merge is always stable. It's normally implemented to access data sequentially, but we can do it with random access also. We wrote the code here with random access. But you could rewrite this with linked lists. You could rewrite it with iterators. You say, wait a minute. How do I get to the midpoint? Well, if it was a linked list, you would get to the midpoint. You'd say, hey, linked list, how big are you? Oh, your size n? Well, I'll move over n over 2, and there I'm at the middle. But hey, remember, you say, hey, that took an extra O of n to get there. Well, that extra O of n goes into, where's our equation? It gets added to this. We would say plus n, because there would have to be the step where I skip to the middle for a linked list, middle of a linked list, and this is the merge. So we'd have one n to get to the middle, we'd have one n to merge. It's still big theta of n log n. So we can still do this in n log n time, even with linked lists. So downside, so that's the advantages. What about the disadvantages? One of the disadvantages is that it is n log n. We will never get better. Whereas insertion sort, hey, if I know my data is almost sorted, then nobody beats insertion sort. The other disadvantage, and now we seldom know that. We seldom know that our data is almost sorted, and when it is, we take advantage of it. But if we don't know anything about our data, we know that merge sort will never be worse than n log n, but it'll also never be better than n log n. The other downside is that merge sort, at least as we wrote it, requires big theta of n additional memory, where quicksort can be in place. Now, you might ask, can't you do a merge with, couldn't you just merge into the same region you're copying from? Well, let's go back to our example here. I've got to go backwards one step. I've got 2, 4, 5, 7, 1, 1, 3, 6. Really, this is one big array, right? It's 2, 4, 5, 7, 1, 1, 3, 6 is all one big array with 2 regions. So I say, okay, all right, let's take, okay, so I'm looking at that one and that one. Let's take the smaller one and put it here, and then I put the 2 here. Oh, now I don't have 2 sorted regions anymore. So, merging in place can be done. There's an algorithm for it. It's complicated. It is crazy complicated. And it is still big theta of n time to do the in-place merge, but it is so complicated that it ends up being slower than using the extra memory. So merging in place does exist, but nobody uses it because it doesn't turn out better. So we need that extra n memory. Well, remember, we've got recursive calls, but I've also got blocks of memory in my vector. Well, again, let's go back to this diagram. When I was near the top, right? When I was near the top of the array, I had regions of size 2. Or really, I'm in the small cases. When I'm in the small cases, I'm near the bottom of the recursive calls, right? So I'm like log n levels deep, and I'm merging regions of size 1 into regions of size 2. So when my recursive depth is the highest, I need the smallest vectors. Then when my recursion works back to the point where I'm near the top of my recursive call stack, now when I'm at a recursion depth of 1 is when I need a vector of size n. So basically my memory requirements, instead of being log n recursion levels deep, is now it's O of n, extra memory. And that encompasses both the recursive call depth and the vectors. Because when I'm at the top of when I'm at the recursive call depth is low, I need the biggest vectors. When the recursive depth is at its biggest, when I'm log n levels deep, I need the smallest vectors. So it takes up, so the downside of this is the O of n extra memory, or really big theta of n extra memory. So there's a little extra time also to copy back and forth, to merge into the vector and then copy the vector back to the original array. So that does take a little bit of time. So quicksort typically performs faster than merge sort. Not always. Sometimes there's inputs where merge sort will do it faster. And you can use merge sort. There's a standard stable underscore sort is a merge sort written in the STL. And stable sort is, hey, it's by definition, it's stable because it's merge sort. It's not heap sort. Heap sort's not stable. But stable sort is a guaranteed n log n sort that's in the STL, and it's guaranteed to be stable. When you do standard sort is what we talked about, what Professor Darden talked about last time. Typically, Visual Studio and G++ use Introsort. Introsort uses a combination of Quicksort. If the region is small enough, it does insertion sort, and if it's doing Quicksort and the recursion depth is bad, it bails out and uses heap sort. But those are not stable. So heap sort's not stable, and Quicksort's not stable. So yeah, when we get to the small regions are stable, but the big regions aren't. So it's not a stable sort for Introsort. The LLVM compiler uses a different sort. You can look it up if you want to. It's called TimSort. Why? Because a guy named Tim wrote it. He named it after himself. Is TimSort stable? I don't know. We're not going to test you on TimSort. Okay, bottom up. So what if you say, hey, Dr. Paley, don't we know that we're going to have regions of size 1 need to be merged into regions of size 2, and regions of size 2 need to be merged into regions of size 4, etc.? Yeah, we do know that. So we could write a bottom-up version of this. So we don't need the recursion. We just need the merge that has its separate vector and some tricky code. So this is bottom-up merge sort. Now, what we expect you to know is what this does. Not the exact code, not how the indices work. The for loops here, what we want you to know is what the for loops are doing, what they mean. But not worry about, well, why does the index start here and end there? Okay, so the outer for loop here says for regions of size 1. So the outer for loop is saying, hey, I'm going to have to take regions of size 1 and then make a call to merge that merges regions of size 1 into regions of size 2. So that's what the outer for loop is doing, is what size are we working on? I'm working on regions of size 1, get merged together. Then it says size doubles. So size doubles. So I say, oh, when I'm done with regions of size 1, let's work on regions of size 2. And when those are merged, let's work on regions of size 4 that need to be merged, etc. So that's the outer loop is determining what size am I working on. The inner loop is working on basically what are the indices of the region I'm working on, right? So if I had something like, what was it? Let me go back to, well, we got it on the next slide. We got it animated on the next slide. We'll go through it together. So basically I is the index that starts out the regions that I'm working on. So like if you think of like when I is at 0, it's saying, hey, I've got 2 regions of size 1 starting at index 0. I've got 2 regions of size 1 that start at index 0, and I need to merge those together. And then I move I, it says I gets plus equaled 2 times size. So it says, hey, when I is 0, I'm working on 2 regions of size 1. When I is 2, I'm working on 2 regions of size 1. When I is 4, 2 regions of size 1. Well, really, it's 2 regions of size. So then when we're later on, we say, hey, I is 0, size is 2. I'm working on 2 regions of size 2 getting merged together. So that's really I sub 0 and I sub 2 are the 2 regions. Then I move over to I equals 4. I've got when I is 4 and size is 2, I've got 2 regions of size 2. Okay, so let's look at this. So there's the code, and here's our array. We think of it as being regions of size 1. Hey, regions of size 1, those get merged together into a region of size 2. Regions of size 1, merge them into regions of size 2. Size 1s get merged, size 1s get merged. Okay, so I go through one pass of size 1s, merge into size 2s. Then my outer loop goes and clicks and says, okay, regions are now size 2, let's merge those together. And I is basically my left arrow here. So this is I, and then it figures out I plus size. Aha, I plus size is where the other region starts. So I do regions of size 2, merge into regions of size 4, move over, those regions of size 2 merge into a region of size 4, and now we go back through the outer loop. Size is now 4. I'm merging regions of size 4. Those two regions get merged, and they go into C, and then C goes back into our array A. So the merge happens, so those get merged into C, C gets copied out back into A, and we've got our sorted merge. Sorry, our sorted array. So we've merged everything back together. So that's the bottom up. Like I said, don't worry about like where exactly the inner for loop starts, the end condition and the min. Don't worry about that stuff. Just big picture. Region size 1 combine into size 2s, size 2s combine into 4s, 4s combine into 8s, etc. Okay, so here's a question. So if I said, I've got a file, it's got 100 million elements in it, I want you to find the most frequent element. Well, first, what you should be asking is, well, wait a minute. Does the most frequent element occur? Like, do we know how often it occurs? Does it occur like greater than half the time? Because if it's a strict majority element, if it occurs greater than half the time, I can use Moore's voting algorithm. Do I know that it occurs greater than n over k of the time, like greater than a third or greater than a quarter? If that's true, I could use Misra Greaves. And they say, nope, you don't know anything about how often the most frequent element occurs. We just want to find it. It might occur twice. And there might be lots of things that occur twice. Just find one of them. But you got to find the most common element, the most frequent element, and I'm not going to tell you how often it occurs. Well, now the only good way to do it is either n squared, like I've got this first value, how many other times does it occur? So I've got one copy of it, how many other times does it occur? So I could do it n squared, and I could do that on disk n squared. I could also use merge sort. If I can merge it, then the merge sort can happen even on the hard drive. It won't fit into main memory, but I can sort it with merge sort on disk. I can get it down to n log n, and then it's a simple, hey, how many in a row do we have? So we could go out and merge sort it on the disk and then check for frequency of elements. When I think I was a senior, I had a class in basically disk-based algorithms and data structures. And that was our first project, was write merge sort on disk files. Like, you've got a file, you're allowed to keep 2 values in memory at a time. That's it. 2 values in memory, the rest of it must live on the disk. And so we basically write the code to take this file, start here, start there, break it into pieces, merge them back, etc. So it's n log n time complexity, and it's n space complexity. We've got to have that extra block of memory. I've got to split it and merge it, etc. I'm going to have an O of n overhead to make that happen. But hey, it's out on disk. We can afford the extra n. Okay, so then there's just a few questions here about merge sort. Can we do it on linked lists? Yeah, it was designed for that. So we can do it on linked list, we can do it with iterators, etc. We've got the merge step. How can it be done in place? Yes, it can. So don't do a how for the second one. Can it be done in place? Yes. Don't go look at the algorithm. It's really, really ugly. But it can be done, but it's just so complex that it's just not as efficient as the extra memory version. The extra memory version beats it in time. Okay, show that both merge sorts are stable if and only if the merge step is stable. Why is the complexity worse than linear? How could it be improved? Well, we could add code to say, hey, is this region already sorted? Then don't make a recursive call on it. So then we could get a better best case, but then our average case would be slower because we'd have, instead of O of n work with every recursive call, set of recursive calls, we'd have 2n work with every set of recursive calls to check, is this region sorted? It's so complicated. There's branch mispredictions, there's cache misses, there's just super complex code where it's got many, many paths to follow. There's so many paths through the code that the branch prediction does poorly. That's why it's so complicated and does poorly. You hit it, Eric. Okay, so we could make the best case better, but it would make the average case slower. And so we don't want to do it. All right, well, that's it for the merge sort. We're done early today. I told you that we would end up with some lectures that ended a little bit early. So we're done early today. Make sure you're making progress on the project. Get the project done. Tomorrow we're going to do the review, and what we're going to do for the review tomorrow is we're going to look at the first part of the slides up to the, hey, what counts as a line of code. Then we're going to go look at the practice exam combined. We're going to do the 2 written problems together, and then we'll go through the rest of the slides, whatever we can get through before we run out of time. And then when noon rolls around, the practice combined answers.pdf will auto reveal on Canvas, and it's got not just the written problem solutions, it's got the multiple choice questions, answers, and explanations below each question. Okay, so we're done. We'll see you after lunch and Prof. SARS at 12:30.